So the time has arrived for us to think beyond the structure of atoms, past chemical bonds and how they form, and start to consider the higher order structures that can result when groups of atoms get together. The scientific community's understanding of chemical bonding began to blossom in the very early part of the 20th century, due in part to the ideas and efforts of researchers like Pauling. Of course, without the ability to actually see molecules and atoms, the path to understanding what holds them together has been a long and arduous one. The work of Dumas helped by providing the first method for determining molecular formulas. But even knowing the exact number of each atom in a given molecule leaves lots of questions. Exactly how are the atoms connected? Are they in a chain? Maybe in a loop? How many atoms are bonded around a central atom? Now let's assume that you're an automotive engineer. How are cars designed and constructed? And how do the various parts combine to form that vehicle? Right? That matters a lot, right? If you're going to do this in a safe, cost-effective way. When you sit down to talk with your fellow engineers, what kind of figures or drawings might you bring along in your portfolio? A flashy color representation like this one? That might work well for the marketing department. But if all you really want to discuss is how the mechanical systems of the vehicle work, you're more likely to use a simplified diagram to foster the discussion. Now, let's take that macro scale analogy and shrink it down to the scale of chemistry. Chemists think of molecules the same way an engineer might think about a car. Instead of transmissions, fuel systems, engines, and tires, we're thinking in terms of atomic nuclei, electron clouds, chemical bonds, and their dipoles. These differences aside, molecules are not unlike machines in our analogy. Just like an automobile, a molecule is a collection of smaller pieces, atoms, that has become something greater than the sum of its parts, because the parts were not all connected together in any old way, but very specifically. Just imagine a car with a steering wheel attached to the radiator and the brake pedal hanging off the exhaust pipe, and you'll start to understand why it's so important to know just how many of each part to use and where to place them as well. So this lecture is all about going beyond simple composition and getting the essential blueprint for a molecule's true structure. If we can do that, then we're halfway to understanding how molecules do the amazing things that they do. Today's task is to get familiar with one of the oldest and still most widely used techniques that chemists use to draw molecules for one another, a drawing style called the Lewis structure. At the turn of the 19th century, an American chemist named Gilbert N. Lewis was hard at work in Berkeley, California. He was trying to understand the relationship between valence electron interactions and chemical bonding. Lewis knew from earlier research that smaller elements have a powerful tendency to seek out valence octets. So powerful is that desire that some atoms are willing to lend their electrons to others in that process of covalent bonding. Lewis had already begun sketching atoms in his lectures at Berkeley using dots at the corners of a cube to depict their valence electrons, a convenient way to demonstrate the octet rule since cubes have 8 corners. As Lewis continued to refine his tool for understanding valence electrons, he began placing the electrons not at 8 corners, but around the atom on 4 sides in pairs of electrons instead. And we'll see why he did this very shortly. He found that this notation style was very useful in his teaching, and he expanded his use of dots to create a shorthand system to track the locations of valence electrons in not only atoms, but molecules as well. Now let's take a look at what Lewis's original mnemonic has become in modern chemistry. Let's start by thinking about the Lewis structures of simple atoms. In fact, let's take some of the simpler atoms available to us, the second row of the periodic table, lithium through neon. Now, if I look at the Bohr model of each of these, it's very simple for me to determine what the Lewis structure should be, because the Bohr model so clearly shows what the valence electron count is. And remember, that's what Lewis was interested in. So taking lithium as our first example, this would be the Bohr model of a lithium atom. It's a 1s2, 2s1, and of course that 2s1 lives out here in the valence shell. So because Lewis structures are only concerned with valence shell electrons, I only put 1 dot on my lithium atom to indicate a neutral lithium atom with a 2s1 electron. If I move to the next element, beryllium, I add a new valence electron for a total of 2, and therefore I put 2 electrons. Now you'll notice that in the beryllium that I've drawn over here, I've separated those 2 electrons and put them on different sides of the beryllium. They can be on opposite sides, they could be at corners the way I've drawn them, they can even be depicted together. It doesn't matter as long as it's the correct number of electrons. Moving along, we get boron, which has 3 valence electrons. And we place those 3 electrons again around the boron in a fashion that's suitable to us. And the trend continues as we move across the row, with carbon having 4, nitrogen, of course, having 5, oxygen with 6, and so on until we reach neon. Now, once we reach neon, of course, we would wrap around and begin anew with only 1 dot on the Lewis structure for sodium. Now that we've mastered drawing the Lewis dot structure for isolated atoms, we can begin to put these atoms together using covalent bonds. Remember that anytime 2 atoms come together to create a covalent bond, they share 2 or more electrons with one another. In a Lewis structure, this sharing of electrons is demonstrated by placing the corresponding dots between the 2 atoms' symbols. The simplest example of this is the Lewis structure for diatomic hydrogen gas, in which the electron for each hydrogen is placed between the 2 symbols. Now, notice that when we do this, we can clearly determine that a single bond consisting of 2 electrons joins those atoms, and that this arrangement fools each hydrogen atom into believing that it has 2 valence electrons all its own. This helps to explain why we find hydrogen as a diatomic molecule in nature rather than as isolated atoms of hydrogen. If we apply Lewis's technique to hydrogen's neighbor on the periodic table, helium, we see something different. The dot structure for isolated helium atoms already shows 2 electrons in its valence shell. This means that helium atoms don't need to bond to one another to fool themselves into thinking they have a 1s2 configuration. They actually do have a 1s2 configuration. So in this case, it becomes clear that helium should exist normally as an isolated atom instead of diatomic molecules, which is in fact the case. And Lewis structures also make it very simple to determine the bonding in relatively simple molecules as well. Let's take a look at a few that we're familiar with already. I have neon, fluorine, oxygen, and nitrogen here, all of which we're pretty familiar with now. We know how they should bond, but let's see how the Lewis structures help us predict. In the case of neon, I have 2 neon atoms. Will they bond? Well, each neon already has its own octet. 8 around the neon to the left here, and 8 around the neon to the right. So I don't anticipate any bond to form here because there is no driving force. But fluorine, on the other hand, will form a bond, and that's because they have to get together to share electrons. We can see very clearly here, this fluorine now believes that it has 8 valence electrons, and this fluorine as well believes it has 8 because of the sharing of those central electrons. Oxygen, similarly, if we look at their Lewis structure, we can tell it's going to bond to try to form an octet. But how? Well, the Lewis structures help me determine that. They show very clearly that in this case, when they form a double bond, oxygen has 8 valence electrons, and the other oxygen also has 8. So we expect a double bond in oxygen. And the trend continues. We go down here and look at nitrogen. When 2 nitrogens get together, we have a triple bond in which the nitrogen on the left now believes it has an octet, as does the nitrogen over here on the right. And when we experimentally verify the bonding behavior of these elements, this is exactly the trend that we see. Now, when we look at these Lewis structures, when bonds form, we often replace the bonding pair of electrons, instead of 2 dots, as a single bar. For example, here with fluorine, these 2 shared electrons in the center would actually become 1 line. In the case of oxygen, the 2 shared pairs become 2 lines, and in the case of nitrogen, the 3 shared pairs become 3 lines. And again, when we experimentally verify this, we see that neon atoms, when they come close, they don't bond at all. You put 2 fluorine atoms in proximity to one another, they'll form a single bond. 2 oxygen atoms come together to form a double bond, and sure enough, 2 nitrogen atoms also come together to form a bond, and in this case, it's a triple bond just as our Lewis structures predicted. But Lewis's invention gives us even more information about the structure and properties of molecules. With all of the electron sharing that goes on in molecules, you can probably imagine that separation of charge is a very real possibility. If all of that electron sharing results in an unusually high electron density around an atom, it might start to feel some negative charge. And if, conversely, an unusually low electron density would arise around an atom, that would make it feel more positive. Chemists have a name for this kind of charge buildup. We call it formal charge. In general, atoms prefer not to carry charge. So if we have a way to scan molecular structures for this kind of destabilizing phenomenon, we can begin to explain why certain compounds are more stable than others, or even how and why certain compounds react. So it would be great if we had a tool for analyzing formal charge in molecules. Guess what? We already do. Let's take some examples here. Let's look at oxygen. Oxygen's electron configuration can be easily defined from the periodic table, 1s2, 2s2, 2p4. This means its Bohr model will look something like this, and its Lewis structure will look something like this. We've seen all of these before. And all three of these representations lead us to the conclusion that oxygen should have 6 valence electrons if it's going to be a neutral oxygen atom. But remember that when atoms bond together, they share electrons. And so there's a potential there for that sharing of electrons to throw off this balance of charge. Now, in an oxygen molecule, the question we have to ask ourselves is this: when an oxygen molecule forms, does each oxygen experience a greater negative charge density than it ordinarily would as a lone atom? And if so, we have to compensate for that. So let's undo that line bond notation and go back to having just dots here showing the bonds so that we can take a good inventory of electrons. And it's very important to make a distinction here. When it comes to the octet rule in bonding, we count bonded pairs as 2 electrons for each atom. But bonded electrons spend a little time on one, a little time on the other, and their charge effect is distributed. So a bonding pair of electrons would only count as 1 negative charge for any given atom that's involved in that bond. Now, what does that mean for oxygen in O2? Well, let's take a look at the oxygen on the left. This oxygen over here on the left needs 6 electrons around it to have its charge balanced from its nucleus. And if we look at our Lewis structure here, we see that we have 2 lone pairs, so that counts as 4 total electrons, and 2 bonded pairs, but those 2 bonded pairs spend a portion of their time in proximity to another oxygen. So their overall effect on the charge is only half of that. And that means that this oxygen over here on the left-hand side, as far as charge is concerned, believes it has 6 electrons. That means its formal charge in this case is 0. This is a happy oxygen. And of course, the O2 molecule being symmetrical as it is, if we do the same analysis over here, we have an oxygen that would like to have 6 electrons. From a charge perspective, it believes it has 6 electrons. Therefore, there's a formal charge of 0. Another happy oxygen. It's getting easy to understand why we see diatomic oxygen down here at the surface of the Earth as its most common form. To highlight that, let's look at another form of molecular oxygen. This one's called ozone, or O3. Now, an O3 molecule would have a Lewis structure that looks something like this. Let's take a look at the oxygen over here on the left-hand side of the molecule. That oxygen should have 6 electrons nearby if it's going to have a formal charge of 0. And indeed, if we look carefully here, we have 2 non-bonding pairs and 2 bonding pairs for a total charge effect of 6. This is another happy oxygen. But things change when we get to the next part of the molecule. Let's look at the central oxygen of O3. Now, in the case of the central oxygen of O3, we have the bonding pairs here. We have yet another bonding pair to its other partner and 1 lone pair for a grand total of 5 electrons as far as charge is concerned. So this central oxygen has a formal charge of +1, and that makes it less stable. Naturally, elements like to be neutral when they can. How about this one over here? We've got an oxygen that has 3 lone pairs and the bonding pair for a total charge effect of 7. Now that means that this oxygen believes it has too many electrons. It's got a formal charge of -1. And we write these formal charges onto the molecules using a circled charge sign. In this case, +1 on the central, and for the structure I've drawn here, a -1 over here on the side. Now it's easier to see why we don't see so much ozone floating around in the atmosphere. It simply isn't as stable as diatomic oxygen. And we can account for that because of the formal charge differences that the Lewis structures predict. So our use of Lewis structures gives us a quick way to illustrate why diatomic oxygen, or O2, is ever present near the surface of the Earth, while ozone, or O3, tends to form only in the most extreme of conditions, like those found in the Earth's outer atmosphere bathed in solar radiation, or in bolts of lightning releasing extreme amounts of energy. We've seen how Lewis structures of pure elements, neon, fluorine, oxygen, and nitrogen, can be used to explain some of their chemical properties. But that only really scratches the surface of what we can do with Lewis structures. Remember that chemistry is about diversity, the study of not just the 100 or so elements, but the virtually infinite library of compounds that can form when those elements are combined. And Lewis structures give us a wonderful way to illustrate the connectivity of atoms in compounds, demonstrating the octet rule and allowing us to predict formal charges in all sorts of compounds. Now, there's a simple trend or a series of steps that we need to follow to construct a proper Lewis structure. The first thing we do is we take all the atoms present in our compound and count the electrons in their valence shells. Next, we place the least electronegative element in the center of our molecule. Then we create a sigma bond network. That means the first bond between the central atom and all the other atoms around it, counting up how many electrons that takes. The next thing we're going to do is fill the octets of our outer atoms with the remaining pairs. And if we have just enough electrons to get the job done, we can stop. If, on the other hand, we don't have enough electrons, we can resort to making pi bonds. And if we find that instead we have too many electrons for this process, we're allowed to expand the octet of the central atom as long as it's in the third row or beyond. Now, that's a lot to digest, and it's probably actually easier to absorb if we do a few problems and learn it that way. So let's get an object lesson now in how to draw a Lewis structure. Let's start with CCl4, commonly called carbon tetrachloride, formerly used as a dry cleaning solvent and commonly used in the chemistry lab today. It contains a carbon and 4 chlorines. We can tell that from its molecular formula. So our first step is to count the valence electrons for all of these atoms. And from the periodic table, we can very easily determine that carbon should have 4 valence electrons and each chlorine should have 7. So my total budget for this procedure is 32 electrons. I'm going to put this up in the corner here so I can keep track as I go. Now, my next step, place the least electronegative element, in this case that's carbon, in the center of my molecule. And create a bonding network that holds all of the other atoms to that central molecule. So, creating the 4 bonds that hold each of these chlorine atoms in place consumes 8 electrons from my valence electron budget. That leaves me with 24 electrons left to satisfy the octet rule for everyone in this molecule. So let's get busy doing that. I'll take all of my chlorines here and fill their valence shells completely. When I do this, I have 6 additional electrons per chlorine, 4 chlorines total. That means I've used 24 more electrons. I've exhausted my budget, but I'm done because when I look at the chlorine atoms, all of them believe they have an octet from a bonding perspective. And when I look at the central carbon, it believes that it has an octet as well. All of the elements, all of the atoms in this compound are satisfied. This is a Lewis structure for carbon tetrachloride. Now let's try another example. How about this one? Sulfur tetrafluoride. This is going to be a slightly different example here. If we go to the periodic table and find the valence electron counts for these elements, of course we find that sulfur usually has 6 and fluorines each have 7, giving me a total budget of electrons equal to 34. Put that up in the corner here and start building my molecule. Now the least electronegative element goes in the center. So which one would go there? Well, naturally, the sulfur, right? Fluorine's the most electronegative element there is. So I'll put the sulfur in the center and begin building my framework. Creating the bonds necessary to hold my 4 fluorines on there consumes 8 electrons, leaving me with 26. Now, just as before, we're going to fill in all the octets of all the fluorine atoms to be sure they're satisfied. That means 6 more electrons per fluorine. And that means I'm going to use, to get them happy, I'm going to use a grand total of 24 electrons. And that leaves me in a predicament. I have 2 electrons left over, but all of the atoms in my compound are already satisfied with an octet. Now, in the unusual case that this happens, and we happen to have an element in the center which is of the 3rd row or larger, just like sulfur is, we have the luxury of packing those extra 2 electrons onto the center. So for this problem, what I'm going to do is take my 2 extra electrons, and I'm going to say, sulfur, I know you'd love to have an octet, but I need you to hold a little bit more for me. And I'm going to put that pair on sulfur, giving it what we commonly refer to as an expanded octet. Again, this is absolutely allowable as long as the central atom is of the 3rd row or below on the periodic table. Okay, one more to drive it home here. Let's try SO3, sulfur trioxide. This is a gas that evolves commonly when coal is combusted and is responsible for acid rain. So we want to understand its molecular structure. Well, we go to the periodic table and we find that a sulfur and 3 oxygens gives us a grand total of 6 times 4 valence electrons, or 24. That's my budget for creating this molecule, so I'm going to bring it on up here into the corner. Step 2, create that framework. Least electronegative element in the center. In this case, sulfur is less electronegative than oxygen because it's lower in the column on the periodic table. And building my framework consumes 6 electrons. So I'm left with 18 electrons to satisfy octets for everyone. Now the question is, can I do it? Well, let's make the oxygens happy, shall we? Let's give them all the electrons they need to believe they have an octet when bonded to the sulfur through a single bond. That's 6 electrons each, right? This one here took 6, this one down here gets an extra 6, and this fellow over here gets an extra 6. Well, that means I've already used my budget, but that creates a new problem, doesn't it? In this case, the oxygens are satisfied, but I've left the central sulfur with only 6 valence electrons. And that's not acceptable for sulfur. It wants 8. So how do we solve this problem? Well, what we do, since there are no electrons left in our budget, we have to take the electrons from a place on the molecule where we've already placed them, make them count for more. And how do you make electrons count for more in the octet rule? You involve them in a bond, right? So let's grab a pair of electrons over here and actually turn them into bonding electrons to the sulfur, creating an SO double bond. Right? So I haven't used any more electrons, I haven't violated my budget, but now when I do my octet analysis, all of the oxygens are still happy, right? Because this oxygen may have 2 lone pairs, but it also has the 2 bonding pairs. But the consequence of my change here is that I've also made sulfur happy because it now has 4 bonding pairs for a total of 8. So when we create Lewis structures for compounds, we have to be very careful to mind our budget, but still try to satisfy the octet whenever possible. As long as we follow these rules, practically any simple compound can be drawn using a Lewis structure. But formal charge isn't the only thing that we have to consider when constructing the best possible Lewis structure to represent a molecule. Just as there are some destabilizing factors like formal charge, there are other features of the electron clouds around molecules and ions which can stabilize them. The most famous and influential of these is the concept of resonance. Chemists owe our realization of the stabilizing effects of resonance to our friends the physicists. In 1926, now famous physicist Werner Heisenberg made the realization that electrons and helium atoms are not distinct from one another. His research had shown that the spin quantum numbers, those that made up the unique address for each electron in a helium atom, could be switched. A single electron could occupy the spin 1/2 position at one time, and then switch places with helium's other electron into the spin 1/2 position at another. Heisenberg's discovery of how electrons can change their positions in atoms forced chemists like Linus Pauling to rethink electron positions in molecules as well. Could a single electron change its position in the Lewis structure of a molecule also? Were electrons and the bonds that they make confined to a specific location between just two nuclei? Or is it possible that electrons could move through larger regions of molecules? Pauli knew that he had to completely rethink the nature of chemical bonding. If electrons could occupy more than one position within a molecule, then there might be multiple Lewis structures that could accurately represent the same molecule. Take the example of ozone again. When we first drew its Lewis structure, we placed formal charges on the two atoms, a positive in the central oxygen and a negative on one of the terminal oxygen atoms. But take a closer look at ozone. We could just as easily have drawn it with a negative charge on the other terminal oxygen of the molecule. Both of these structures depict an ozone molecule of similar stability, similar bonds, the same amount of charge separation. So, which one is the correct one? The answer is neither of them. In truth, ozone would be better thought of as a molecule with 1.5 bonds on each oxygen and 1/2 of a negative charge on each terminal oxygen. This is the result of electrons moving throughout the molecular system. Since those electrons are no longer confined to a specific bond, we call this phenomenon delocalization. When we study ozone carefully, this is exactly what we see, a molecule whose behavior is consistent with this sort of average of the two structures that we first created. One where delocalizing bonding electrons creates a molecule that can't quite be modeled using just one Lewis structure. This phenomenon, in which electrons become delocalized and move through a molecule's bonding system, is generally referred to as resonance. In this case, two resonance contributors can be mentally averaged to give us a so-called resonance hybrid, a better description of the molecule's true structure. Now, notice that the two resonance structures are encased in brackets and separated with a double-headed arrow. This is our way of conveying that they are two different representations of the same molecule and not a chemical reaction taking place. So, just 25 years after Gilbert N. Lewis first scribbled a few dots on a blackboard in his Berkeley classroom, his structural scheme had grown into a standard method of depicting the electronic structure of molecules. One that helps us explain not just the connectivity of atoms and molecules, but their stabilities as well. So let's summarize what we've learned today. We met Gilbert N. Lewis, a renowned American physical chemist working at the turn of the 20th century in California. We saw how Lewis devised a shorthand method of drawing atomic structures that depicts only the valence electrons belonging to an atom as dots surrounding the elemental symbol for that atom. Next, we saw how atomic bonds can be shown using Lewis structures by placing shared electron pairs between those atom symbols, either as a pair of dots or sometimes as a line. This method of drawing, combined with the octet rule, gave us a simple way to explain why hydrogen exists as a molecule, but helium does not. Next, we used Lewis structures to demonstrate why certain elements tend to make single, double, and triple bonds to other atoms of the same element. And after that, we took a look at the concept of formal charge. And we noted that accumulating charge is usually a destabilizing factor in molecules. And Lewis structures allow us to survey structures for that charge. Finally, we discussed a stabilizing factor known as resonance, a phenomenon in which multiple realistic Lewis structures known as resonance contributors can be drawn for the same molecule. And we saw how these resonance contributors can then be mentally combined to create a more realistic depiction of the compound called a resonance hybrid. Now that we've mastered conveying the connectivity of atoms and molecules, it's time to take the next step and think about how those connected atoms are arranged in space. Molecular geometry is up next.